Okay, everyone. It's 4 o'clock, so about time to start. And today we are really happy to have our own Dr. Betty for the water seminar. So I just want to quickly go through his background. I think everyone knows him very well. Well, Dr. Betty joined our department since 2013, and he received his undergrad in civil and environmental engineering from BYU, and also he got his master from University of Guam, which is a very interesting experience. And then he came to CSU to get his PhD, and then he stayed here as the assistant professor, associate professor, and now already full professor. So he has done a lot of great research, including like the watershed management practices, and also using numerical model to inform some management practices for environmental systems, and also develop some really cool, very useful groundwater model for us to use. So I don't want to spend too much time to go through all his excellent background. So just give him a big hand and welcome him for the center.
Well, it's really nice to be here today. I can stand here, right? Is that okay?
Sure.
All right, with you, Al. So we do a lot of work with model developments, groundwater models, watershed models. I'll just share 2 examples today about how we use these models as decision support tools to answer some engineering questions. And I'm going to start pretty basic and then kind of build up from there in case anyone here has not done hydrologic modeling before or is familiar with that. And first I'll talk about what is a hydrologic model, go through some theory and some basics, and then two applications, one in Western Colorado about flood versus sprinkler irrigation and how the aquifer interacts with the river in those situations. So that's called to switch or not to switch. And then the second case study is in the Chesapeake Bay Watershed. Are we there yet? Meaning, how do we figure out the nutrient management problem? And when might we see some results when we manage nutrients in these large river basins? So first of all, hydrologic models are used to predict responses of hydrologic systems to stresses. So we have a stress and a response. And of course, back in dynamics, we learn from Newton's second law of motion, that everything that has a stimulus, there will be a response. So the basis of all physical applications of motion, what is the response of an object to a stimulus? So we have an object, we apply a force, we're going to have a change in motion, often a change in velocity. And of course, Newton's second law of motion, F equals ma, but we arrange that and we have a stimulus, force times a delta, a time step, and then we get a response from that. And everything in physics and with motion is based on this very nice application and rule. So of course, this is the version that we're often familiar with, F equals m times acceleration. Now, when we talk about hydrology, we have different systems we're looking at. So we have lakes and reservoirs, we can have a wetland, soil profile, an aquifer, or a aquifer system, streams and rivers, and then estuaries. And what we're trying to figure out is based on all these stresses, so we have inflows and outflows, and we have a small lake as an example here, precipitation, evaporation, groundwater exchange with the aquifer, and maybe a discharge from a point source. Those are the stresses, and we want to figure out what is the response from those stresses. And so response could be, what's the volume of lake water? What's the stage, the surface area? All those can change when you have these stresses that are applied to the system. And of course, how do we relate stresses to responses? We have conservation of mass. And so we're going to look at the change in volume, for example, how much lake water we have with respect to a change in time, equals all the inflows minus all the outflows. So a very simple water balance. And we can rearrange this. Not sure why they got cut off on the bottom. We can split apart that delta V into an old volume and a new volume, for example, over a daily time step. And the new volume equals the old volume plus this inflow minus outflow times that time step. We're just rearranging this to figure out what's the new volume after, for example, a day. And inflows and outflows, we have all these stresses that go into that very simple, this is the Euler's method to kind of forecast into, you know, 1 day, or it could be a week or a month, whatever our delta T is chosen to be. And that is in its kind of basic form, a hydrologic model. So for example, if we apply this to John Martin Reservoir in Colorado, this is Southern Colorado, Arkansas River flows here and then out here through the dam. We also have some tributaries. And if we're trying to figure out the change in volume, or the volume of that reservoir through time, we can apply this very simple water balance. So for example, we'll have the Arkansas River come in, we have the Purgatory River come in, and we have outflow. We also have some rainfall on the surface area of the lake, and then we have evaporation off the reservoir as well. And so if we apply the water balance to this, we have a starting volume, and as long as we know on a daily basis these inflows and outflows, and we have maybe a weather station for rainfall and evaporation off the open water, we can simulate the change in volume, or the volume through time, of the reservoir water. And the red dash line, that's what the model is giving us, just using a spreadsheet on a day-to-day basis. And then this is what's measured. So the USGS has a gauge here which tracks stage, and we convert that to volume, so we can make sure that we have our model that is compared with our measured data. So that's working pretty well. In addition to the response, that's the volume of water in the reservoir, we can also track all these inflows and outflows through time and see how they compare to each other. So for example, this is water flux, cubic meters per day. We have, stream 1 is the Arkansas River, stream 2 is the Purgatory. We have rainfall, outflow through the dam, and evaporation. You can see how those relatively compare to each other through time. And of course, if you have on a given day more inflow than outflow, you get an increase in storage, and then vice versa if you have more outflow than inflow. If you take in my 542 class, you did this on one of your homework assignments. So this is very familiar to you. Now let's look at an aquifer. So here's our water table. This is an unconfined aquifer. We have a well here that's monitoring the water table, and we have a stream over here. And if we're interested in how much groundwater we have, we can do the same approach, treating this aquifer as a control volume. Welcome. Good to see you guys. For now, for an aquifer, we have stresses. We have recharge coming in from rainfall or irrigation. We can have pumping that is extracting groundwater. Canals can seep. That's going to be a source of groundwater. We can have an outflow, discharge to streams over here. If you have a higher water table than the stream, then you have outflow. Or if you have a lower water table, you can have streams that seep water and recharge the aquifer. So these would be our main stresses on the aquifer. The responses would be how much groundwater do we have in cubic meters? What is the head or the water table above a given datum? And what would be the flow rate of that groundwater flowing through the aquifer? Again, a very simple hydrologic model to figure out, here's our new volume equals the old storage plus all the inflows minus all the outflows over a time step, for example, a day, a week, or a month. Now, here's a very simple system. And if you've taken 423 groundwater engineering, this is a problem that we work through. Treating this as a single control volume, here's a starting water table of 30 meters above a datum. And here's a very simple representation of a stream. And that stream stage is at 28 meters. So to begin with, on the first day of the year, the water table is 2 meters above the stream stage. So we're going to get some of that groundwater going into the stream through discharge. We also have recharge, could be from rainfall or from irrigation, and we're going to have some pumping. So we have 3 things going on. There's going to be exchange with the river, there's going to be recharge coming in, and pumping leaving. And so each day we're going to track the inflows and outflows to figure out the change in storage, or how much groundwater we have in our aquifer. So here's our groundwater volume. We start here with 30 meters, and this is kind of a surface area. So we have a starting volume. And then initially, we're going to have the storage decreasing because some of that water is going to be discharging to the river. So it's going to be a gaining river, but the aquifer is losing water. And then we're going to start pumping. So this is like the growing season. Maybe we're growing a crop here and we irrigate. So we're going to pump. So we decrease our storage because we're pumping. And when that happens, it drops the water table low enough that now we start having the river seeping water into the aquifer. So it's going to change directions. And so now we have groundwater storage is increasing because we have seepage coming in from the river. So just a very, very simple example. You can still understand and explore how the system responds to just 3 different stresses on our system. This is showing the water table. So it starts at 30 meters. It's decreasing because water is discharging to the stream, and then pumping drops it rapidly. But then here it rebounds because now we're getting water seeping into the aquifer. And that 28 meters there is that stream stage. And we're assuming for this problem that the stream stage just stays at 28 meters for the whole year. When you get some more advanced modeling, of course, that can change and as a boundary condition. But just another very simple example of how to apply a hydrologic model of the water balance to one of our systems. And here's fluxes. So here's pumping is in green, so that's leaving the aquifer. Recharge, those are some irrigation events coming in. But then we have river exchange. At first, it's negative because it's leaving, and then we start to see some positive because it's seeping water into the aquifer. So just, again, a very simple example. Now, if we want to get more complex, we can divide our aquifer into different multiple control volumes. So here we could have 1, 2, 3, 4, 5, 6 control volumes, or we call those grid cells or aquifer sections. And we can write this equation, apply it to each of these sections for each of our daily time steps or weekly time steps, whatever we choose for delta T. So each of those, we're going to look at the storage from the previous day and update it based on the stresses happening for that individual section. So now if you have a pumping well, maybe it's right here, and this cell will respond to that pumping well, and you'll remove groundwater, drop the water table, and that will induce flow from nearby cells because now you have a gradient. So this is how you can now take an aquifer, divide it into multiple sections, multiple grid cells, and apply this very simple water balance equation to track groundwater volume and groundwater head throughout the aquifer in these local sections. Here's an example. This is kind of looking down on an aquifer plan view. Very simple, unconfined aquifer. Here is a stream, and now we divide our section into this checkerboard or grid where we have rows and columns. And now we're going to apply the water balance equation to each of these grid cells for each of our time steps. And now we can track groundwater volume and head spatially through an aquifer. Of course, when we can even go to 3 dimensions. So now instead of having a checkerboard just in 2D, now there's also layers. And for each of our grid cells, here's the interior cell, we apply our water balance equation, recharge coming in, we could have pumping leaving, we can have lateral flow using Darcy's law that goes inflows and outflows laterally through our aquifer system. So these models, when you get large, like hundreds of thousands of grid cells and layers, it seems complex, but it's really every cell is just applying a water balance every single day, inflows and outflows. So for example, one of these modeling codes is MobFlow from the US Geological Survey. And this is using a structured grid here with multiple layers to define different geologic units. And here you have an unstructured grid where maybe near a pumping well or a canal or a river or maybe a reservoir, you can refine the grid so that you have smaller grid cells. So you can track kind of the change in head or change in storage locally at the points where that might make a difference in groundwater flow. But again, this is a finite, looks like a finite element mesh here. But again, each node or element is you're applying a water balance for every time step. It always comes back to just some very simple algebra. If you look at a stream or a river, same thing. Here's a channel, and stresses might be, inflows and outflows, precipitation, evaporation, groundwater exchange, point source discharge. You could also have like diversions for canals or water treatment plants. Anything that's affecting how much water you have, you can apply it to your water balance equation. Responses would be how much water you have in the river channel, stage, surface area, flow rate, kind of like lakes and reservoirs. Now, if we want to look at the whole watershed, we have, for example, 5 different types of systems we're looking at: lakes and reservoirs, wetlands, the soil profile, aquifer, stream, river. But for each of those, the same thing, you're just doing a water balance for these individual control volumes. And when you look at watershed, you can have water going from one of these components to another. For example, when you have rainfall and irrigation applied to the soil, you can apply a water balance to the soil profile, and the output can become recharged to the aquifer. So the output from one can become the input to another, or discharge from the aquifer is an input to the stream. But again, each of these, you apply a water balance on a daily basis. And a lot of models out there for like the soil and water assessment tool, SWAT or SWAT Plus, HEC HMS, all of these are applying these water balances on a daily basis. So I'd like to now that's our background, look at two different cases where we're applying these hydrologic models. And in the second one, we're doing actually pollutant transport, and I'll talk more about that theory when we get to that second one. So the first one I'll talk about is flood versus sprinkler irrigation in the White River Valley. And to give some context, of course, this is showing kind of the size or how much flow in the different rivers in Colorado. And we're going to go to the White River, which is in this White Yampa River Basin here. And that White River is going to flow through a town called Meeker and flow out, eventually get to the Green River in Utah. All right, so here's all the irrigated fields in Colorado, zooming in to this area near Meeker. Here's the town and these green area. This is the irrigated field. There's about 300 fields, mainly grass, pasture for livestock, a little bit of alfalfa. But the White River starts up here in the mountains and flows out here through Meeker and then out to a town called Rangeley and eventually over to Utah. We have two main aquifers, Agency Park Aquifer and Powell Park Aquifer. They are highly conductive alluvial aquifers, often up to like 800 feet per day for hydraulic conductivity. So very, very nice sand and gravel aquifers. Here's some pictures here, just a beautiful, gorgeous area. A lot of people come here for fishing and for outdoor experiences. And here's the White River that flows, and here's through the town of Meeker. All right, here's the problem statement, and this is typical of any alluvial aquifer river valley where they've done flood irrigation for several decades. This is typically what you'd see. So here we have our river. Of course, for us, it's the White River. We have inflow coming in from the mountains, and we have fields that we're going to be irrigating. And there's often a ditch that's going to be applying just through gravity drainage, applying that water. But you're going to have a ditch diversion go into this. So you divert water from the river, go into this ditch. You're going to have some of that water that seeps from the ditch bed into the underlying aquifer because it's often just earth and material under the ditch. The remainder is going to be applied as this flood irrigation. Of course, you want a lot of that water to sustain crop evapotranspiration and crop yield. But a lot of that water actually is going to seep, bypass the soil profile, recharge the aquifer. It's going to raise the water table and induce flow back to the river through groundwater discharge. So here's a cross section of that. In the spring and summer, you're going to apply irrigation water, also some seepage from the ditches. That's going to raise the water table, and it's going to induce flow back to the river in the fall and winter months. This is called late season return flow because it happens typically after irrigation has stopped. So really what's happening in a lot of these systems is some people might call it wasting water because it's not being used by the crops, but it is recharging the aquifer, goes back to the river eventually, and can be rediverted downstream. So it's really just recycling the water, where the aquifer acts as kind of this bank of water that slowly releases it back to the river. So the question is, in a lot of these places, they're thinking, should we switch to sprinkler because it's more efficient on the field? If you switch from flood to sprinkler, what will happen to the magnitude and timing of these groundwater return flows to the river? And what will happen to the river flow in the fall and winter months? There are reasons why you want to have flow in the winter for environmental flows, fish populations, downstream hydropower, riparian areas, ecological benefits. And if that goes away, people are worried that in the winter and fall, all that's is gonna disappear. So we want to figure out what will happen. A little more detail about this area. So this is the irrigation type applied to each field. The red is sprinkler. So there's a few fields that do sprinkler, but mainly it's flood irrigation. And I've been there when they flood irrigate and they just, they divert water from the ditches through these little small dams, and it just floods the field, and they have some surface runoff and recharge that's happening. All right, so again, White River. So what we think is happening, and this is, this is a few years ago before we started the study, we thought that the aquifer, just a lot of that groundwater that's recharged from irrigation is going to flow back to the river here in the agency park from south to north and here from north to south in the Powell Park area. So how much groundwater enters the White River? Where and when does this occur? How do ditch diversions and groundwater return flows affect stream flow? What would happen if you convert to sprinkler irrigation? So two main approaches we did. One was we first want to just learn about the hydrology of the river aquifer system. Before we get to scenarios, learn about the system, what's really happening. So we use some field data. We put in 11 monitoring wells to track water table with a data logger. And then another method was there are several USGS flow gauges here, and we could do a river water balance to figure out how much groundwater is coming into the river on a daily and monthly basis. Then we want to figure out with the groundwater model some more details of river groundwater interaction, what's happening in the individual fields with irrigation runoff and recharge. And then finally, once we have a model that works properly, we can use it for scenarios. What will happen if irrigation switches to sprinkler? We could also use the model to do other what if scenarios. What if a drought happens? What would the recovery like? What if there was a call on the river downstream and they had to turn off some of these ditches? What would happen if there was less diversion into these ditches? So a decision support tool, and I'm going to talk about now about how we develop that. So first, though, the field data, we looked at the years 2019 and 2024 to learn more about hydrology. These orange dots here, 1, 2, 3, 4, are USGS gauges where we have daily stream flow. We also have, for all these ditch diversions, there's about 30 ditches here. We know those daily diversions well because they have to report that to the state, and you can download that data. So for each of these sections, we can do a water balance on the river and figure out how much groundwater is coming in. And what we found is that for this first section, on average, about 40 CFS, about 20 CFS for the section 2, and again, about 40 CFS for section 3. Doesn't seem like a lot. Total is about 100. And here's kind of a time series of all the groundwater coming in on a daily basis. Positive means groundwater is going into the river. Negative would mean there's some seepage happening. So this is just when you aggregate that, you get about 100 CFS on average. But the outflow in the river itself is only 585. And so a large portion of this river flow is groundwater coming in. It's about 20%. And it does change through the year. But we need to know, first of all, like that's a pretty significant portion of river water that is coming from groundwater. So about 20%. So the second method we used to learn about hydrology was to develop a mod flow model using, here's a grid of 200 feet by 200 feet. Again, for each of those individual small grid cells, we're doing a water balance for each day using mod flow. Some features, we're doing ditch seepage to the aquifer. So these red lines are the ditches. So we're simulating seepage into the aquifer along those lines. And then we have recharge from rainfall and irrigation for each of these fields. And we use a soil water balance method to track deep percolation and recharge to each of our grid cells. There's some pumping. Meeker uses pumping for drinking water, so we include that in the model. And then we want to simulate the exchange between aquifer and tributaries and exchange between the aquifer and the White River. For all the grid cells that intersect the river, we can calculate those exchange rates. To do this, we developed a new irrigation package for mod flow that tracks daily diversions, daily canal seepage, soil water balance. So you could apply this more realistically for a study area like the White River. Model testing. Again, we had those 3 sections where we can get groundwater exchange with the White River. So make sure that the model gets those same rates. Water table elevation at the 11 monitoring wells, make sure that the model is tracking water table fluctuation properly. And they also, for the Highland Ditch and the Miller Creek Ditch, the summer of 2024, they did a canal seepage study. So they knew what the seepage rate was, so we could have that as a final test to make sure our model was getting the same seepage rates. So here's what the model is giving from 2019 to 2024. This is after calibration. And this is just looking at the daily river fluxes. So what is affecting the White River on each day. And so this gray that's just inflow coming from upstream at the USGS gauge. Green is diversions. So notice how each year there's 2 diversions. That's because they're cutting hay and then they do another diversion set. So each year you have 2 diversion times. And then the light blue is how much groundwater is going back into the river. So you can see that the timing is, they divert, they irrigate, a lot of recharge happens, and then that drives flow back to the river. So you have these same, every year, that kind of seasonal pattern. And then we have this yellow is how much groundwater gets into the creek, into the tributary. So, but mainly it's groundwater getting into the White River as a response to the diversion, which recharges the aquifer. So this is looking at our water balance. It's kind of busy here, but this is how much water is coming in. This is in millions of cubic meters per year, but it's all relative. So upstream is 505, you divert 163. And what we really care about is a lot of that goes into the soil or to the aquifer through discharge. And then we get a lot of discharge back to the river. So you're diverting 163 from the river, you're getting back like 133. So each year, 30% of the river water is diverted to ditches, 25% seeps to the aquifer. That's the seepage right here. Combined with this seepage, about 88% of diverted water recharges the aquifer, and 80% of diverted water goes back to the river. So you take out a unit or 100 units from the river, 80 units are going to come back through this return flow. And typically that's happening in the fall, winter months, these late season return flows. And notice here, crop ET is only about 40% of diverted water. So the irrigation efficiency is really low, which might seem like a bad thing. But the water goes back to the river and it gets used downstream. So you're not wasting it, it's just being reused downriver. Okay, so I already mentioned those things there. So now we can look at some scenarios, and we want to look at first, what would happen if you change the sprinkler? And then second, what would happen if you eliminated kind of human influence? So what were the natural conditions like before they irrigated? And they started about 120 years ago. So before irrigation, what would conditions be like? And here I'm showing direction of groundwater flow. This is historical, meaning what we feel like actually happened using our data. Again, here's the White River, and you can see the groundwater flow. This is a map of water table elevation, and with these contour lines, flow is going to go perpendicular to that. So you have these the groundwater is flowing towards the river. That makes sense. That's what we're seeing with the data and with the model. Now, if you change the sprinkler, and when you change the sprinkler, you don't need as much water on your field because you're more efficient. And so you're going to divert less water from the river and apply. So you still have the same crop ET, you just don't need as much water because you're not going to have runoff and recharge that's going to be off of those fields. So we found that typically, or we feel like you're going to have about 40% of your historical diversions. And so you're going to have less recharge. So your water table drops. You're not going to have much reach or discharge back to the river during the fall and winter months. And we're seeing this with the model is that when you do a sprinkler scenario, now the groundwater is flowing kind of parallel to the river. You do have some points of discharge, but it's going to be a lot lower. And under the natural conditions, no diversions. So the only recharge is coming from rainfall. There's almost no flow back to the river. So most of this is just parallel. Groundwater is flowing in, still flowing in the aquifer, it's just not going into the river. You do have a little bit of natural flow from groundwater to the river, but a lot of that is gone now because you don't have as high of a water table. This is the Powell Park aquifer over on the west side. Again, historical, you see these flows going in. Sprinkler, still kind of there. Natural, there's almost no flow into the river. It's all just parallel flow in the aquifer. Another interesting thing that happens is it retimes the river flow. So this is looking at the downstream gauge out of the study region. And this is baseline is black. And I'm going to zoom in here in just a second. In fact, I'll do that right now because it's kind of hard to see. So here's the summer months. This is our baseline. This is under flood irrigation. If you switch to sprinkler, you will have more flow in the summer because you're not diverting as much water. because you don't need to because you're more efficient on the field. So you keep more water in the river in the summer months, but in the fall and winter, you're going to have less flow. Again, black is baseline, blue is sprinkler, less flow because you didn't build up the water table. You're not having much groundwater flow back into the river in the fall, winter months. So you just kind of switch how things, the timing of river flow. Higher flows in the summer, lower flows in the fall and winter. And under natural conditions, this is all like the snow melt coming in for the summer, higher flows. Again, you're not diverting it. There's no irrigation under natural conditions. But now you're going to have less flow in the winter because you don't have the return flows. So it kind of flip-flops and its retiming. So the question is, do you care about more flow in the summer or more flow in the winter? And it's up to the local water managers what they really care about. Do they want to sustain river flow or do they care about summer flows? And just retimes it. And this has been shown in other irrigated regions. When they switch from flood to sprinkler, they see a retiming of your flow rate. So it's our second diversion period. That's post irrigation, and that's when things will switch. Now, another thing is what would happen to wetlands. This is a map of current wetlands in the area just from the National Wetland Inventory, national database. And what's interesting is you do have wetlands along the river, but you have also a lot of wetlands just near the irrigated fields. And these are artificially created wetlands from flood irrigation. They're there only because we're irrigating. But just because artificial doesn't mean they're not beneficial, right? So we want to figure out what would happen to those wetlands under the sprinkler scenario and the natural conditions scenario. And this is a drop in water table in meters under the sprinkler condition. So red is more than 5 meter drop in water table. Orange is 2 to 5 meters. Yellow is 1 to 2 meters. And if you look at kind of intersect that with the wetland map, we feel like about 20% of those wetlands are going to be gone. They won't be maintained because all these wetlands are from irrigation and also from they're based on a high water table. They're groundwater dependent. So you get rid of surface runoff and recharge, and you're going to have 20% decrease in your wetland area. Now, natural condition is even lower, and it seems about 80% decrease. So there were wetlands here before, but irrigating with flood irrigation has greatly expanded how many wetlands we have. So a lot of people are interested in preserving those wetlands. So they want to keep that flood irrigation going. So here's just some general conclusions. Basic hydrology, okay, we kind of already went through this, but of the water diverted from the river, 80% is replenished by groundwater discharge. Half of that happens in July, September, 1/4 during the fall, and then one fourth during the following spring. Flood irrigation moves water to the soil and aquifer, high groundwater storage, high groundwater discharge, and maintenance of wetland areas. So if you're going to decrease those diversions for sprinkler natural conditions, you're going to decrease groundwater discharge to the White River. You're going to retime river flow, more flow in the summer, less flow in the fall, winter. And then you're going to have a decrease in wetland areas. So a lot of these, again, this is what we're showing, and now local managers have to decide what they do, right? Do they keep with flood or they change to sprinkler? Most of the local farmers and ranchers want to keep flood. They feel like there's a lot of benefits to that, which we're kind of showing with this study. Okay, now moving on to pollutant transport. Again, we talked about these hydrologic models for these systems, but we can also track pollutant mass using the same process. So instead of looking at volumes of water, we're looking at mass of constituents, for example, grams or kilograms. And now the response would be, what's the mass of a pollutant in our lake water and the concentration? Just taking mass divided by the volume, so you get concentration. So it's same process. We're looking at the change in mass with respect to time. We have all the mass coming in through all these stresses and all the mass leaving through, for example, stream outflow, and so forth. So same process. And again, if we want to calculate the mass at a new time, we look at the old mass plus the change in mass times the time step, and we figure out what's the new mass. And then concentration is the new mass divided by the new volume. And we have these concentrations that we can look at and see how they compare with targets that you want for different pollutants. So now we have a water quality model in addition to hydrologic models. So now when you apply this to watersheds, again, you have this mass balance that you apply for the pollutants to the lakes, the wetlands, the soil, the aquifer, the streams. It all gets stitched together because inputs or outputs from one become inputs to the other. We can look at the movement of nutrients, nitrogen, phosphorus, salts, heavy metals, toxic substances, pesticides, and apply those to different watersheds around the country and around the world. I'd like to focus on the Chesapeake Bay watershed. This has been in the news a lot, actually for decades, because of eutrophication that happens in this Chesapeake Bay because of it's draining this big agricultural area, nutrients from point sources, from non-point sources, right? Inorganic and organic fertilizer and dairies, and that results in algal blooms and eutrophication in the Chesapeake Bay. You have these dead zones that happen because of lack of oxygen as it gets consumed by dying bacteria and microbes. And so this is the problem that we're trying to, the scientists are trying to figure out how to solve that. So we have these different catchments: Susquehanna, Potomac, James River, York River. Here's the Western Shore. All these watersheds that drain water and nutrients into the Chesapeake Bay. We need to target those with conservation practices and then see how that can help the problem in the receiving waters of the Chesapeake Bay. So we're going to zoom into this West Shore here and look at a watershed called the Chesapeake River Watershed. And here it's flowing out. So it flows kind of north to south here. And we have two catchments. One is called the Tuckahoe Creek Watershed, and one is this Upper Greensboro Watershed along the Chesapeake River. And what we want to do is figure out, can we apply conservation practice to these farms here and reduce organic fertilizer, inorganic fertilizer, and have it make an impact in the water quality of concentrations of nitrate and phosphorus in this bay, which then goes into the Chesapeake Bay. So 400 years, right, of ditch drainage. So you have tile drains, which collects soil water and groundwater, and that's kind of a fast way for those nutrients to get from the fields into the Chesapeake River and Tuckahoe Creek. Shallow groundwater, so that's also a way for nutrients to get into the receiving waters. And they have been applying conservation practices: reduced tillage, winter cover crops, manure management, riparian buffer enhancement, drainage management. And the question is, are these working, and when could you see a result in the downstream waters? However, some problems that we're finding there and also elsewhere in the country is that, you know, you're going to apply conservation practices to the land surface and you're trying to see a result in the downstream water, but there's been decades of fertilizer application. And so you have nitrogen and phosphorus mass build up in the soil. It leaches to the aquifer, and it could take a long time for that groundwater to reach the stream, years or decades. So this is called legacy nutrients. And you can imagine that even if you make a change here, you may not see a change in the stream because you have decades of this groundwater. It's loading over years and decades, kind of slowly flushing out. And so you might say, well, we put in millions of dollars to implement conservation practices. We're not seeing any change downstream. It's because it's going to take a long time with these legacy nutrients being slowly flushed out of the system. The problem is a lot of the models that we use to test conservation practices do not account for that slow travel time of the groundwater, because they're treating groundwater as kind of a simplistic reservoir system instead of physically based, like I'm showing here, using a water balance approach. So when you say how to mitigate the problem and you apply conservation practices, you want to use models to figure out the impact of those, and our models aren't being properly constructed. So that's what I'm trying to show here, is how to do that. All right, I already talked about that. All right, so here, the nice thing is we have the USDA ARS, so Ag Research Service. They have an office in Betsville, Maryland, and they have gone out and done a lot of field data collection, tracer testing to figure out some of these travel times just based on field data. So what they found is in the Chesapeake River catchment, the mean residence time is about 17 years. So to go from the field to the nearby channel, almost 2 decades for that travel time to happen. Tuckahoe River catchment, a little bit less, only about 10, 11 years. And that could be based on the aquifer conductivity and how quickly the groundwater can move through those systems. So typically when you make these models and you have hydrology, you test for stream flow, make sure the model does stream flow right. You test for groundwater levels. And the last thing that people are not doing that we should do is test for groundwater travel time in the aquifer. Once you do that, then you can test for nutrient transport and then run scenarios of conservation practices. If you miss this step, you're going to use the model and get wrong results. And then you're going to tell stakeholders that, hey, we should see results in a few years. And when it doesn't happen, then they think everything is wrong and they regret giving you money to look at the models. So we're trying to make sure that even if it's not the answer they want, we're still getting it correct because that's the real system. So again, we want to track groundwater residence time, and we're going to use a watershed model called SWAT Plus, the soil water assessment tool created by the USDA. And over the years, we put in a new groundwater module that is tracking based on a water balance for different grid cells. And so we feel like it's a more physically based, realistic system. We have soil water balance channels, aquifer, and then we also have nutrient application, storage, and transport. So here's the SWAT model. And the red boundaries are Huck 12 catchments. Those are our subbasins. You can see the stream network. And here we have a structured grid for our groundwater module, but we're doing something new now using an unstructured grid where you can have these base grid cells, but near like tile drains and channels, you can make the cells smaller. And so you do a water balance on a more local level and you can get a better gradient. And especially if you want to track groundwater travel time, you have to get the gradient of the water table correct. So that's why we're doing this unstructured grid approach. So we have a base value of 500 meters and you can locally refine your grid down to like 50 meters along the tile drains and channels, or even smaller if you want to. Now, for each of these, we're also tracking travel time. So for each time step, we figure out how far the groundwater's traveled from a starting point, and you can track its pathway to a receiving tile drain or channel, and then you can track how long it took to get there. And then we want to make sure that the model is giving the same travel time that the tracer data was giving for the field data, and then we can use the model for conservation practices. Okay, so here's a result. For each of our grid cells, this is the time to reach the nearest channel or tile drain. This is in days. So you can see when you get right near a channel, it could get there in a few months. But as you get farther from a channel, it could take a few years to get there, or even a decade. Now, we want to relate this back to to the fields where they're actually applying the nutrients. So we do a spatial joining GIS to each field, and we figure out for each field how long it would take the groundwater under that field to reach the nearest tile drain or the nearest channel. And so, and then again, same scale here, or a little bit different scale, but blue is 1 year, 2 years, 3 years, 4 and 5 years. And now for this Chop Tank or Greensboro watershed here, we can take the average of those, make sure it relates to the tracer data from the field for Tuckahoe here. And what we're finding is Tuckahoe, our median value is 17 years. You know, I think I got those switched on the previous slide. It was, so the Tuckahoe was 17 years or 16 years, and this one was 10 or 11 years. Sorry about that. But what we're showing is in yellow, this is what the model's giving, and this is what the tracer data is giving. So now we're making sure that the groundwater has the right travel time from these fields to the nearest channel based on this tracer data. So now we can use this for conservation practices. And these are looking at individual flow paths. So for example, if you take this location right here, it looks like it's going to go to this channel, but based on gradients, it actually flows south. It's going to hit this channel right here. And that takes, over 30 years to get there. So you can have all these different pathways of from fields to the channel, and then how long it takes to get there. Make sure it matches up with our tracer data in the field. And this is kind of zooming in, looking at some individual tile drains and channels, some groundwater flow paths there. All right, so now next steps. Salam is here, and he's going to do this. He's a postdoc working with me. Right now he's calibrating. Now the travel time is working. It's great. So now he's going to calibrate and test them all for nitrogen and phosphorus in the channel network and the aquifer, and then use it to quantify the impact of nutrient management practices using the correct travel time in the aquifer. And then we also have other applications for different watersheds in the Chesapeake Bay watershed and try to kind of combine all these to get some patterns to show results of these, what happens with these nutrient legacy or legacy nutrients in these watersheds. So some concluding statements. Hydrologic models can be constructed for any hydrologic system. Hydrologic models can be applied to engineering problems in the natural and built environment. They can assist with decision-making, for example, irrigation practices, whether you switch or not, and mitigating nutrient pollution in the correct way, accounting for travel time. So just a couple examples we're working with right now in our research group. And thanks for your attention. I'll take any questions now.
I think we have time for a couple of questions. Anyone, yeah.
Yeah, great presentation, and thank you. On Chesapeake Bay, it looks pretty bad. It's gonna take so long, but what about surface runoff? Would there be much impact to the surface runoff that would give us some results quicker?
Yeah, so phosphorus doesn't usually leach to the aquifer, and so for phosphorus, it attaches to sediment, and that's more like runoff driven. You probably would see a change in phosphorus more quickly, but nitrate is what typically leaches to the aquifer. So probably long term for nitrate, short term for phosphorus. That's the hope anyway for phosphorus. Yeah, and some watersheds are phosphorus impaired, not nitrate impaired. So that's actually good news for phosphorus, but not for nitrate. Great question, Grayson.
How would you implement the travel time in the aquifer if you don't have that field data, like the studies they did? Or would you just have to get it?
You have to, like, you need the tracer data.
Yeah.
Yeah.
Okay.
So they have, I didn't talk about that because it's a lot of chemistry, but it's called MESA. It's an herbicide byproduct, which doesn't undergo any chemical reactions in the aquifer, so it's a nice tracer. And the USDA has maybe 40 sites across the country where they've collected this data. So they have travel time for those 40 watersheds. There's some in Iowa, Minnesota, Ohio, Indiana, mainly Midwest and then East Coast. Yeah. But it's taken a lot of years and a lot of money for them to get those data sets. But it's cool that we have them now to assess this. Yeah.
Yeah, kind of the follow-up. So did they really track the tracer data for such a long time, like 10 years, 16 years? So that means that they're right now still tracking the data?
Well, they're still collecting the data. They're not they haven't been collecting for that long. So they take measurements in the river, and the herbicide that they're looking at changed chemical formula in the year 2000.
Mhm.
And so if they look at ratios of different products in
Gotcha.
the herbicide, they
Gotcha.
can figure out, oh, this was old water versus new water.
Gotcha.
And that's how they're getting some of these
So
estimates.
kind of the estimate.
It's an estimate for sure.
Gotcha. Based on the prior time.
Yep.
Gotcha.
But at least it's something.
Yeah.
That we didn't have before.
That's true.
Yeah, great question.
So about your hydraulic model, how did you estimate or quantify the hydraulic activity in each cell if you don't have enough geological forward data?
Right. So we have geologic maps that we have different aquifer zones, and based on material type, we provided an initial value of hydraulic conductivity. And then we use model calibration to calibrate for stream flow. And we also have groundwater head measurements from the USGS. So we are using conductivity as a calibration parameter as we try to get these targets of stream flow, groundwater head, and then the travel time. So, but we try to keep it in a reasonable range. If it's a sand material, make sure that we're not going outside the bounds of the sand, but there's still orders of magnitude that you can play with. So it works pretty well. Oops, there. Yeah.
These two less some biological processes happen, so the nitrates could be converted, so it doesn't, we don't have a lot of change in it.
Yeah, so there are definitely certain go back here. So some of these are intended to kind of change the microbiology of the soils and riparian areas to enhance denitrification. Yeah, so and it's not here in the model, but you can also do like permeable reactive barriers and like aquifers that it's expensive, but they do try it if there's an area with a lot of local pollution. They might do that, like a groundwater plume of nitrate. Yeah, mainly though, I think for the Chesapeake, they're doing more like land surface application or conservation practices. Yeah. Great question.
So you said like, we just kind of have to do it to get accurate results, but have you gotten responses from stakeholders at like different levels, whether it's farmers or government agencies in the Chesapeake Bay, and you've told them like, oh, well, we actually have to collect way more data for way longer, and we have to model it, and there's uncertainty in that model. And then we can maybe evaluate these practices that are already taking a bunch of time and money. And like, what has generally maybe been the response, or what do you expect it to be? And like, where do you see it going forward? And if there will be like truly, decades long support for studies? Like, what's your take on it?
Great comments and question. So I'm not in those conversations. The USDA provides us with funding to work on, to help them with the modeling. But I mean, this has been going on for decades now with the EPA, and they funded a lot of people to work on these models. And I think there's some frustration, of course, that we're not seeing more benefit. But I think showing the science at least there is uncertainty. You can't get around that, and this is going to take a long time. Like if we have decades of pollution, it might take decades of mitigation. It's not like a quick fix. I think they understand that, but it's still frustrating, right? Because it's a lot of taxpayer money to provide conservation practice money for these farmers to implement. And then they're not seeing as much. Like the Chesapeake Bay is still really, really bad. So yeah, it's hard to get around those real questions, those real facts though. Yeah.
If you have any, what were like some of the most surprising like things you guys came across from empirical data? Like what were some like, if you had any like variables that like had more of an effect on the watershed than you were expecting? And like if there were any,
That's a good question. For like the hydrology or for like the nutrient stuff?
I don't know. I guess both. Like if there's any variables like flow rates or mass or whatever. Like
Mhm.
I don't know. Like however the water flows to the rivers and how that dissipates through. Like, is there anything that you guys were not expecting that you showed in data?
Yeah, so I didn't show it here, but in these two catchments, there are hundreds of tile drains, and we weren't expecting that many. Like we were kind of saying, oh, there's probably some tile drains here, and then a local agency gave us like a GIS shapefile of all the tile drains that we had to impose into our model, and you realize it's just bypassing. So back to Sandra's question, even if there were some things you put in the aquifer to kind of like mitigate nitrate, those tile drains bypass that. It's like a quick way to pollute the channel. So I was kind of surprised at that because I've heard of tile drains, of course, like in Iowa, we use it for modeling, in Ohio. I didn't realize they were here, and it's just another complexity that's causing pollution. So great question. That's one thing that I can think of right now.
Maybe one last question. So has this project already considered the downstream impact from the tide? Because Chesapeake Bay is actually a coastal region.
Oh, yeah.
So you can think about when they got a high tide and you kind of change the.
Like down here.
Exactly. You kind of change the groundwater head, like comparing to the original one that you have in the inland water.
Yeah.
So you probably will have a shift of the direction for the groundwater
Sure.
discharge.
We haven't looked at that. We're mainly focused on kind of these upper areas where most of the farming practices happen. And they've been collecting also like, phosphorus and nitrate data from surface runoff, just from the fields. If you want to get down here, you would probably use a more sophisticated groundwater modeling approach that could have, not only change the gradient, but also there's density differences because you have water and fresh water, and that can sometimes drive flow based on the density difference.
Right.
We're not accounting for that here. I think other groups have done that for this place and other regions as well, but tides definitely can have an impact. Yeah. Right.
All right. So let's thank again to Dr. Bailey for excellent.